let's try to solve this problem here. A 60 kg bungee jumper jumps from a bridge. Okay, so it's a bungee jumping activity that you usually see in their videos. Okay, she is tied to a bungee cord that is 12 meter long. So bungee cord is the spring cord that you see that is hanging the human. Okay, then they fall with the bungee cord usually. Okay, when unstretched. Okay, so when unstretched means like the original length of the bungee cord is 12 meter. Okay, if you stretch it, then you get longer than 12 meter. Okay, then you say that the bungee jumper falls a total distance of 31 meter. So you can see that before that, when it is unstretched, the bungee cord is 12 meter, but when you drop, it falls a total distance of 31 meter, right? So the spring or the cord stretches from 12 meter, which is the unstretched length, stretches to 31 meter. So it stretches by total amount of 19 meter. Okay, 12 meter unstretched length plus 90 meter of stretching, it will become 31 meter of total length of the stretch cord. Okay, so now they ask you to calculate the spring constant of the bungee cord and the maximum acceleration. Before we try to solve anything, let's try to sketch a situation first. I think I can imagine it to be a 3-step process. Okay, so let me try to sketch the 3-step process here. Okay, so first you have your human or the bungee jumper on top. Okay, let me draw a common ground first. First, the human is on top, and the cord is also on top. Okay, so this is the initial situation. Let's call it as A. Okay, what happens after that is the bungee jumper has already jumped, but the spring is still unstretched yet. Okay, so over here, you are already eyeing already. Okay, but at this particular situation in point B, what happened is the length of your spring is still unstretched yet. Okay, so this is still 12 meter long, unstretched. Okay, then from here onwards, your spring will start to stretch. Okay, let's draw situation C. Your spring will already be stretched and you will reach your maximum total distance that you can travel. So now you reach this point. If you reach the maximum distance or the total distance 31 meter, what happened is that's the lowest point you can go, right? So if you think of a spring when it's stretched to the maximum, what happened is the object will stay for a little short moment at the lowest point, then it will spring back up, right? If you fall to the lowest point, then it will spring back up. So at that lowest point over there, your friend, this bungee jumper here, will stop momentarily. Okay, and that momentarily stop, if you measure the length of the spring here will become 31 meter. Okay, then afterwards, I believe you know what happens. Afterwards, this friend over here will spring back up. Okay, so it falls this way. Okay, once it reaches the maximum length already, the spring reaches maximum length, then it will stop momentarily, then after that it will spring back up. Okay, so you can, if you are not sure how to imagine it, you can probably go find a video of people doing bungee jumping. You can see the person will jump, fall, reach the lowest point possible, then after that it will spring back up a little bit. Okay, so this is a situation. We have already break it into a 3-step process that we want to investigate. Okay, now they ask, what is the spring constant of the bungee cord? Okay, so means by this spring over here has a spring constant of K, and you're interested to find it. Okay, K can be related to the force experience, the force, restoring force of the spring. S spring over here can be equals to Kx. Okay, if you ignore the direction, then it's F is equal to Kx. If you wish to think in terms of energy, you have your elastic potential energy, UEL, or U spring. is also equals to half kx squared. So that's where you apply the spring constant in your syllabus. And I believe since you are doing a question which involve falling, you have change of gravitational potential energy. And when the person is falling, the speed is changing, so it will involve kinetic energy. And because there's spring being stretched and unstretched, you have also the elastic potential energy. So it's a change of the kinetic energy, gravitational potential energy, and the elastic energy throughout this whole journey. But you know that throughout this whole journey over here, your mechanical energy should be conserved. Okay, so because you know the mechanical energy should be conserved, you can say that the mechanical energy at one point A over here can be equal to the mechanical energy at point B, can also be equal to the mechanical energy at point C. Okay, but we are interested with the spring constant of the bungee cord, so definitely you want to compare it with a position in which there is elastic potential energy. You know that the spring is unstretched over here at A, the spring is also unstretched here at B. The spring is only stretched when it is in situation C. So you know that definitely you need to compare it with situation C. But you compare which point with situation C? You compare it with situation A. Because situation A, you still haven't moved yet. You know that the kinetic energy is 0. You are still at the maximum height, the highest point available. So if you set that as your reference height, then your reference height can immediately become 0. Okay, then you know that the spring is unstretched, the elastic potential energy is 0. So technically you know all the information when you are in situation A, but you're interested to find the spring constant during the journey, and this spring constant can only be found with a stretched spring, which is in situation C. So you compare situation A with situation C. So let's do it. So for question A, we are going to compare the mechanical energy at point A with the mechanical energy at point C. If you expand it, the mechanical energy will be consisting of kinetic energy, gravitational potential energy, and also elastic potential energy, all at position A. Whereas for C, you have your kinetic energy at C, you have your gravitational potential energy at C, and also elastic potential energy at C. So if you expand it, should I expand it? Let's don't expand it straight away. Let's try to analyze first. At position A, you are not moving, you haven't jumped yet, so your kinetic energy should be equals to 0. At the same time, if you set this platform over here, or the bridge over here, if you set it as the reference height, or h is equal to 0 over here, then essentially at position A, you are standing at the reference height. So your height will be equal to 0 over here. So if your height is equal to 0, your gravitational potential energy will be equal to 0. Okay, so this is because VA is equal to 0. This is because HA is equal to 0. Whereas your spring is unstretched, so your XA is equal to 0. So therefore, all three energy at the initial position A is equal to 0. Okay, but we know that when you are in situation C, you also momentarily stop as well, because you are ready to be bounced back in the opposite direction. So you are making a U-turn, going from going downward, change to moving upwards. So there's a change of direction of motion. You have a momentarily stop in order to make that U-turn. So because there's stop over here, there will be no kinetic energy, because your VC here is also equals to 0. Okay, but now you know that you are below the reference height in situation C. You are below the reference height, so there will be a gravitational potential energy. At the same time, your spring is also stretched. In fact, it's stretched to the maximum, so there will be elastic potential energy. So these two terms need to be expanded, but the other four terms here all equals to 0. So now we may continue with our expansion. So this one because 0. This one will be 0 plus mghc plus half kxc squared. Okay, so now we expand already. Let's proceed with substitution. The mass over here is 60 kg. That's the mass of the bungee jumper. 9.81 for our acceleration due to gravity. Then you have your HC. HC, you can measure from the reference height to the height of the person over here. And because it's below the reference height, this 31 meter here should attach with a negative in front of it because it's below the reference height. If it's above the reference height, then the height will be a positive value. But now it's below, so this will be negative 31 meter. Okay, continue, plus half k. K is what we want to find. But x over here represent how much of stretch happens or how much of compression happens over here. So if we look into the situation, this is the unstretched length, whereas this is the stretched length. Okay, so the difference will be this length over here, and you can measure it, it will be 19 meter. So this is how much stretch that has happened to the cord over here. So you can substitute in your x over here to be equals to 19 meter square. Okay, so now there's only one unknown left. So if you proceed to key into your calculator, you'll find the spring constant to be equals to 101.09 Newton per meter. So that is the spring constant of this spring over here. Okay, next, the maximum acceleration experienced by the jumper. To explain this situation, probably it's good that we sketch a free body diagram for situation A, B, and C. Okay, situation, there's no need to draw a situation A actually. B and C will help us illustrate the situation clearly. Okay, when you are at point B over here, what happened is the spring is still unstretched yet. Okay, if the spring is still unstretched yet, when you draw your free body diagram, you still have your weight of the bungee jumper, but because the spring is not stretched yet, there is no force exerted by the spring. You need to have stretch in order to have restoring force. Okay, so because there's no stretch yet, there will be no restoring force exerted by the spring. So right now, you can consider situation B here to be similar like a free fall situation because there's still no pull by the spring yet. Okay, but as you continue from B to C, what happened is the spring will stretches. Okay, the spring stretch. So your F spring here will slowly increase. Why does it increase? Because your X is increasing, the amount of stretch you have is increasing, therefore your F spring is increasing. Okay, so it increase until a point where you are at C. When you're at C, you still have your weight because the person still have mass, but what happened is you have a very big, you have your maximum F spring over here. F spring max happen over here, and I believe you can see that F spring max here, I've drawn it to be very long compared to the weight, because the F spring, the restoring force exerted by the spring, is actually larger than the weight. And because this restoring force is larger than the weight, you know that your net force will be pointing upwards, and because your net force is pointing upwards, therefore your acceleration is pointing upwards. Okay, your acceleration is pointing upwards, but your motion is going downward. You are falling, but your acceleration is pointing upwards. That's why, because they are opposite direction, that's why you are slowing down. But technically you have already slowed down until point C, you already slowed down to a stop. Okay, so because the acceleration and the motion are in opposite direction, you are slowing down, and when you reach point C, you have already slowed down to a stop. Okay, so where do you find maximum acceleration? Well, the maximum acceleration has to be at point C. Why it has to be at point C? Because over here, your F spring is maximum. So F spring maximum minus W will generate the largest net force you can see throughout this whole journey. Okay, throughout this whole journey here, what happened is F spring will slowly increase. You increase until a point where F spring will be equal to W, but you still continue to grow. This F spring will still continue to grow until you reach F spring max. Then at this point, it will be larger than W. When it's much larger than W, then you find maximum net force pointing upwards at point C. Okay, so point C here will be the point where you have maximum acceleration. Okay, so the net force here will go from W pointing downwards, slowly decrease to the F spring cancel out the W at some point in the middle, and as you continue to progress, this F spring will largely exceed W, then your maximum acceleration will be pointing upwards. Okay, so let's try to solve this question by finding the maximum acceleration at point C. Okay, so you need to find the net force at point C, and it's equals to 0. It's not equals 0, equals to ma, because you know that you cancel out the weight heavily and you still have a net force pointing upwards. So it's equals to may at point C. So you take the force in the same direction as acceleration, which is F spring max, minus the force that is in the opposite direction to the acceleration, which is W. So you have your F spring max minus W, and is equals to MAY. Okay, you can expand the F spring to be equal to Kx. Again, we are not going to put in negative Kx, because if you put in negative, that means that you're talking about the direction. But I already checked the direction using the sign already. Follow acceleration, positive. We already checked the direction here to be positive. We already checked this direction here to be negative. So we don't need to include the negative Kx in the negative inside anymore. Okay, because we already checked the direction over here. Okay, continue. Minus the weight will be equals to mg, and this will be MAYC. Okay, we can change the AY over here to be just AY maximum. You can change it to be maximum here, and you can say that this is the X when it's maximum as well. Okay, so now you have already do your expansion. You can proceed with your substitution. K does not change throughout the journey. It's still the same spring. You're not changing the spring. Your X maximum over here, you already know that it's 19 meter. You already stretched for an amount of 90 meter. Minus your mass is 60 kg. G is 9.81. 60 kg. And now you're left with your AY maximum. So you can key into your calculator, and you find that the maximum acceleration that you can find will be 22.2 meter per second. Okay, 22.2 meter per second is much larger than the weight. Okay, so you can see that the maximum acceleration here far exceeds the weight of the object. Okay, what I'm trying to say is the weight over here, it's equals to mg, right? This mg here is only 9.81, but you see that the acceleration that you're having at point C here far exceeds the acceleration due to gravity. That's why this is the maximum value, not 9.81. Okay, your maximum acceleration is 22.2 meter per second. That's about 2g. Okay, about twice of g. So you feel a force of pulling you upwards. That force almost exceeds twice the gravitational pull that you're experiencing downward. Okay, just the little understanding of what's happening here. That's about 2g, a strong pulling force holding you, pulling you back upwards. Okay, so that's how you solve this question involving a person falling. It will be a combination of kinetic energy, gravitational potential energy, and elastic energy. So that's all for this question. Thank you very much.